So, give it up to Aimee.
Okay, so I want to start off with this quote. A language that doesn't affect the way you think about programming is not worth knowing. How many of us dismiss CSS because it's just a markup language? It's not a programming language like JavaScript. But I would like to argue that it does affect our thinking, whether it's like cuss words that we say to ourselves or something like that. It does affect the way we think about things. And everybody has probably seen this GIF. It is like the most popular CSS GIF out there. This is how we feel, whether we are trying to fix someone else's CSS or write our own CSS from scratch. So a little bit more about myself. I work for Warner Brothers Digital Lab. So if people have heard of like Batman, things like that, I work for Warner Brothers. I am a panelist on the podcast called JavaScript Jabber. I used to do Angular Air. I also was a competitive figure skater for most of my life. I spend a lot of time in the gym outside of programming, and I also spend a lot of time running. I have 2 cats, so I like my 2 cats. I drink a lot of hot tea, and I also drink a lot of kombucha. Okay, so why am I talking about CSS to a room full of JavaScript and Angular developers? First, because I think knowledge of internals are really important for advanced debugging and performance tuning, which comes to my story a little bit, why I did this talk and why this is important to me. So I spent, like Carmen said, I am still a somewhat new programmer. I spent most of my time at doing full stack JavaScript for the first 2 years, and it wasn't until a year ago that I switched to only doing front end. And I realized when I switched to that role that my CSS skills were really pretty poor. I felt pretty good about debugging my JavaScript, but when it came to CSS, I felt like I was just blindly throwing darts at a dartboard most of the time. It was a lot of guessing, and it wasn't systematic like when I was debugging my JavaScript. And when you work for a company like Warner Brothers or Disney or something like that, it's not like when I was doing most of my front-end role. In that role, it was like the JavaScript just needed to work, and the JavaScript was what was important. But when you work for a company like Warner Brothers, the CSS is very important because it's their brand, so it is almost as important as the JavaScript. Because if you're off by a pixel, it matters to them. Also, why I want to do this talk about CSS to a room full of Angular and JavaScript developers. In the future, we're going to be able to modify the browser's rendering engine, which is what I'm going to talk about. We're going to focus on the rendering engine today, but on the next slide, you're going to see that in the future, we're going to be able to actually hook into that. So there's this new task force that's being formed. It's called Houdini. How many people have heard of Houdini? Some people. Okay. Not that kind of Houdini. So it's a task force from different browser vendors, and what they're doing is they're working to expose a set of APIs so we can hook into the internal rendering engine. And you might think, like, we have things like Bootstrap, but those just avoid cross-browser differences. They don't actually normalize them. And with Houdini, you're also going to be able to invent or polyfill new features. So we can think of Houdini as like jQuery for our CSS or Babel for our CSS. Finally, this. I just think low-level programming, I don't know how it is for you guys, but for me, it just feels good to like go really deep into something and understand it. So you might ask, can't I just use component-based styling? That's probably the most popular question right now when I give this talk. So I think component-based styling is really good. You're going to gain specificity, and that makes things easier, but you're going to lose the cascade. CSS is not JavaScript. So as JavaScript developers, like global variables is a code smell, but in CSS, it's actually a good thing. Because imagine if you didn't have any global variables, you had to go into every single component and change the color of something if someone told you to change it from like this shade of red to another shade of red. But if you have a global variable, you only have to change it in one place. So with component-based styling, you're gonna lose that. You want to be able to use component-based styling and regular CSS. You're also unable to affect children classes by their parents. So again, you're losing the cascade. So what we're going to talk about, I'm going to start out by talking about the browser's internals. Once we get done with that, we're going to go into the rendering pipeline and talk about the parsing process. And then I'm going to get into some more practical things. So we're going to talk about debugging specificity, positioning, and Zindex. So how do browsers actually work? Let's look at the different components of the browser. So first, if we broke it up, you have the user interface layer. And that is just things like the address bar, your backward and forward button, your bookmarking menu. Then you have the browser engine, and that's just a mediator between the user interface layer and the rendering engine. And you have the networking layer, so that's responsible for making your HTTP requests. So like as you're reading your HTML page, you need to eventually go and fetch some things from that. Then you have the JavaScript engine, which some people don't necessarily realize that the JavaScript engine is very different from the rendering engine. You have the UI backend, which is actually hooking into your operating system and drawing things to the screen. And then you have the data persistent layer that just as a high level is managing things like cookies and local storage. So let's start and talk about how the DOM is actually formed and go on a deep dive there. So the first thing that happens is we don't actually receive HTML, obviously. We actually receive these raw bytes. And we receive those raw bytes either like off of your local disk or off of the network, and that process is actually called conversion. Once you have those raw bytes, then those bytes are translated into individual character codes based on the file encoding, so the browser knows if it's parsing an HTML page or a CSS page. Those characters are then further broken up into individual tokens. That's done via the tokenizer. So it knows that it needs to break up those inputs into valid tokens. So it's going to be things like start tags, end tags, attribute names, or attribute values. And it's smart enough to know that has to strip irrelevant characters like white space and line breaks. It's a lot like building out an AST for JavaScript. And a lot of times if people talk about lexing and tokenizing is really kind of the same thing. So the output from the tokenizer is eventually going to look something like this. Then those emitted tokens from the tokenizer are converted into individual object nodes. From there, the parser is going to read the stream of tokens and analyze the document structure according to the language grammar. So grammar meaning the vocabulary and syntax rules. The parser then compiles the source code into this tree structure here, which now you finally have your DOM. Something to note about the DOM, though. So the DOM, when the browser is parsing your HTML page, it has to be smart enough. It has to take into account the surrounding characters for the individual character it's on. And that's what we mean by it not being context-free. It has to have context when it's parsing that individual character, what's around it. And if we think about it, the reason it has to be that way is because the browser, we all know when you give it ill-formed HTML, it's going to render it no matter what. So if we want to visualize that, I'm going to visualize that the browser is actually looking something like this when it's parsing our HTML. It's an unconventional parser. It's not a smooth process, and it can be very choppy if we give it ill-formed HTML. CSS, on the other hand, like JavaScript, it's a conventional parser. So I like to imagine it like I try to be when I'm skating. It's a very smooth process. You give it the same input, you're always going to get the same output. So to wrap up that section, before we get into the main flow of the rendering engine. So the browser first sends an HTTP request for that HTML page. Web server sends it back. The browser is then going to convert the raw bytes of data into tokens. Then those tokens are turned into nodes via the tokenizer. Then the browser turns the nodes into the DOM tree. Then once the DOM tree construction is finished, by default, the browser stops. And that's when it has to actually form the CSS object model. How many people have actually heard of the CSS object model? Not very many people. That makes me happy, actually, because that's how I was. So we're going to drop down into this section. Again, so the first time I heard of the CSS object model, I was like, what in the world are we talking about? I know what the DOM is. That's one of the very first things you learn in JavaScript because you're ultimately manipulating the DOM with JavaScript. But the DOM and the CSS object model are completely different data structures to the browser. But again, the CSS object model is going to look ultimately kind of like the DOM. It's this AST kind of thing, or tree structure. But as with our CSS, the browser needs to go through the same thing. So it needs to convert the CSS rules into something the browser can work with and understand. So the browser is going to repeat that same process it did for the HTML for our CSS. So what the browser does is it goes and fetches the HTML page. It starts reading through the head tag, and it's going to encounter a link tag if you've included a style sheet. And at that point, the browser needs to go and fetch that style sheet. So that's the point where everything stops by default. Now, you can tweak that, but by default, CSS is treated as a render blocking resource. So it's going to hold off of any parsing until that CSS object model is constructed, which, if we stop and think about it, that makes sense for two reasons. So the first reason is, it would be very jarring for the user if we went ahead and painted everything to the screen and then we fell down into the cascade and potentially changed the layout of things or changed the color of things. So the browser needs to stop until the entire CSS object model is constructed. The other reason is if we went and fetched all of our JavaScript right away before the CSS object model was constructed, a lot of times our JavaScript is reaching for things within the DOM, and CSS can reorder the DOM, CSS can change the color of the DOM. With CSS, we're adding classes and things like that. So we don't want to, by default, the browser wouldn't by default want to go ahead and fetch the JavaScript right away. So again, we repeat this process for CSS. And ultimately, when we arrive at the CSS object model, we have the style sheet objects, and the style sheet objects then contain a CSS rules object. Within the CSS rules object, then we have more CSS selector and declaration objects and other objects that go along with the CSS grammar. And if we want to imagine what this is looking like again, so to compute the final styles for an object on the page, the browser is going to start with the body tag, and then it recursively applies these nodes to get more and more specific with our styles and follow along the cascade. And the CSS object model is not one-to-one with the DOM. So anything that's not visible to the screen, like script tags, meta tags, your head element, those things that are not in the actual reflected output, they're omitted from the CSS object model. And you can think that the DOM captures the properties and relationships to the document markup, but it doesn't actually tell how things should look when they're rendered to the screen. That's a responsibility of the CSS object model. Things with like visibility hidden, though, those do appear. So now that we have the DOM and the CSS object model, let's go over to the render tree. The render tree is just a tree of visual elements in the order in which they're going to be displayed based on the CSS object model. So the render tree is really just a mashup of the CSS object model and the DOM. It's going to be a visual representation of the document, and it's going to enable painting of things in the proper order. The CSS object model can have really drastic effects on the render tree, but it has zero effect on the DOM tree. And that's because the CSS object model can actually reorder nodes. So the purpose of that render tree is that it knows how to lay out and paint each node and then anything that is a sibling of that node. It's going to include geometric information like the width, height, and position of each node. And each node in the DOM tree that has visual output has a corresponding object in the render tree. So if we want to imagine how the render tree is formed. So we start at the root of the DOM tree, and we're going to traverse each node. The browser is then going to omit the non-visible nodes. For each visible node, it's going to find the appropriate matching CSS object model rule and apply it. Then each visible node gets the content and computed styles applied, and we're going to ultimately output this render tree that contains both the content and the style information of everything on the page. Okay, so now that we have the render tree, we're going to go into the rendering phases. So we have layout, paint, and composite. So now we're here. Just like with our JavaScript, though, you can inspect this in your developer tools if you open up the Performance tab. Layout, depending on which browser you're looking at, is usually called Reflow as well, and it's just calculating the position and size of all of the render tree objects. And the output of the layout process is a box model that contains the position and size of every element within the viewport. After layout, we run paint, which again, you can inspect in your developer tools in the performance tab. Paint is often called raster sizing. A lot of times, if you're looking at Chrome, which would be Blink, that's their rendering engine, they call it raster sizing. And it's converting each node in the render tree into actual pixels on the screen. The browser's usually going to go through multiple rounds of painting for different reasons, a lot of times because our JavaScript coming and loading things that are changing the DOM structure. And painting this makes sense. It includes things like text, colors, background shadows, things like that. Painting time, obviously the bigger the width and height of an element, the longer it's going to take. Adding different effects obviously is going to increase your painting time. And it's important to note too, if we look at that rendering pipeline, painting is usually the most expensive thing. So if you want to look at the performance of your CSS, this is where I would start. I also found this really interesting. So someone took a floated layout and they measured it, and it rendered in roughly 14 milliseconds just for the painting time. And then they converted it to Flexbox, and it sped up to 3.5 milliseconds. So I find that, myself included, a lot of JavaScript developers or Angular developers were really excited about learning new things in JavaScript or in Angular. But when it comes to CSS, we're not so excited about it. But I'd argue that if we care about our sites being performant, we also need to pay attention to the CSS. So it pays to keep up with your CSS skills. And then painting order. So the order that things are painted is going to fall in line with how the elements are in their stacking context. And I'll talk about stacking context when I get into Zindex. But it's really from backwards to front. And painting can be global or incremental. So the browser is smart enough, if you look at this GIF I made, to know that only certain areas of the page need to be repainted. So the browser is smart enough to know that it marks an individual section as invalid, and it's a dirty region then to the browser, and it's only going to generate a paint event for that section. So as you see here, like if you open up the developer tools and enable this, you can see as I hover over the navigation, it's changing from black to blue, and the browser has to render a paint event, but it knows that it only has to render it for that region. Finally, Composite, which is something that's somewhat new to browsers. Just like with everything else and with your JavaScript, you can inspect this in your developer tools if you add the Layers tab. So the Layers tab is not there by default. You'd have to go in and add that. And what Composite is, I'm sure everybody here has heard of hardware acceleration, but I know when I first heard of it, it was kind of a buzzword. I didn't actually understand what it meant. And hardware acceleration is what compositing is. So rather than using the CPU, compositing allows a browser to hook into your GPU to render things. So it's essentially taking the painted parts that were in the process before and putting those together. It's rendering different elements of a web page in different layers, and it's the action of flattening those layers into the final image. So to talk about rendering performance, so different things that you do to the DOM and different properties that you add are going to affect your rendering performance. And depending on what you're doing, you don't actually have to hit layout, paint, and composite. You can pick and choose, and obviously it's going to be most performant to only do composite. But adding a DOM node is going to cause a relayout and repaint of the parent node. Major changes like increasing your font size is going to have to relay out and repaint the entire tree. Changing an element's color, there's no need to run layout there. You're only going to generate a paint event. And if possible, you always want to pick transform or opacity, because currently those are the only properties that only trigger composite. You don't need to do a paint for those. So to summarize this section, as you guys saw in that GIF that I had, the browser is smart enough to do the minimal possible changes in response to an action. And layout is always going to trigger paint, since changing the geometry of an element means the pixels need to be resized. So we always want to avoid layout if possible. Okay, so now that we've been pretty theoretical, I want to get practical, and let's actually talk about the proper way to debug specificity. So I'm sure this has happened to everyone. It happened to me before a lot. So you move something around on the page and something else, an entirely separate section of the application breaks. And maybe you don't even see it until like a week later. But I had this thought last year, and it was really interesting to me. So when I first started programming, CSS seemed really easy. It was JavaScript that I was scared of. I would just add like an inline style to something and change the color, and it was no big deal. But as I got more advanced, I felt like JavaScript was the part that I was really confident in, and CSS was the scary part to me. And I saw this quote, and I kind of thought to myself, it was time, whether it be because I had switched to a front-end role or this too, and I thought, it's really time that I feel as confident with my CSS skills as I do my JavaScript skills. So specificity, it sounds really simple. If multiple CSS selectors are targeting the same set of HTML elements, and we are applying the same property or properties to that HTML element, the selector with the highest specificity value will win. But I have a quiz to see how good we are at actually calculating this. So I have this small section of markup and these associated styles, and I want people to guess what color the anchor tag is going to be. I'll give people like 30 seconds. Does anybody want to like raise their hand and give a guess? Orange. Orange? Pink? Anybody else have a guess? Orange. We have a lot for orange. Pink. Another one for pink. Okay. So the answer is pink. Does anyone know why it's pink? What the actual value is? I'll keep going, and I'm going to explain why this is. So the value is 111, but it's important to remember, so it's the commas are there to remind us that it's not a base 10 system. You can think about it like it's 111, but you would possibly have things like 13 or something that starts with a 0 where it's not going to spill over like a base 10 system. So a lot of times, if I'm starting out doing this, what I'm going to do is actually draw out a table. So why it's pink? First, if you have an inline style attribute, that's going to get 1,000 points. Obviously, we didn't have that at all. The second column, you're going to count up the number of ID selectors, and that's going to give us 100 points. The third column, you're going to count up the number of class selectors, attribute selectors, and pseudo classes, and that's going to give us 10 points each. And then finally, for the final column, we're going to count up the number of type selectors and pseudo elements, and that's going to give us 1 point each. So the people that guessed orange, so you can see now why it's pink, not orange, because the type selectors and pseudo elements, those only count for 1 point. So in our case, in the third column, we got 10 points there, so that's why we won on that one. So positioning. It's the process of determining the position and size of all boxes. It goes back to the layout process that happens before paint. For normal, the object is going to be positioned in that render tree according to its place in the document, its box type and dimensions. For relative, it's positioned like usual, and then moved by the required delta, meaning if you give it like top, right, left, or bottom, it's going to be moved according to the value that you set there. For float, the object is laid out in the normal flow and then moved as far left or right as possible. For absolute, the object is going to be put in the render tree in a completely different place than it is in the DOM tree. As with a lot of things with the browser, because of the cascade, layout is a recursive process, but width and height are computed a little bit different for positioning. So width is computed based on the current render object, but height is based on the children. So for each child, the current render object is going to determine the position of the children, and it asks the children to compute their dimensions. Then the current render object can compute its height based on the children. Okay, next up, Zindex. Again, this sounds really simple at first. Every element in an HTML document can either be in front or behind of every other element in the document. And elements with a higher Z-index are stacked in front of elements with a lower Z-index. Sounds super simple. It's rarely that hard, though. And I know for me, it appeared so simple that I learned, factually what it was, but I didn't go any deeper into it. How many people have heard of a stacking context? Only like 3, 4 hands maybe? Wow. Okay, good, good. I'm glad I can help you guys, hopefully. Okay, so the key to understanding your Z-index issues is all about understanding stacking context. But what is a stacking context? It's a 3-dimensional representation relative to the user facing the screen along this Z-axis, so this way. And it's a group of elements that are going to move forward or backwards along that Z-index together. So every stacking context has a single HTML element as its root element. And when Z-index and position properties, because you have to have a position property other than static applied, aren't involved, the rules are simple. The stacking order is just based on the order of appearance in the HTML. So again, it has to have that position property like relative or absolute. It can't be static. And you can have a root stacking context and then a local stacking context. So a root stacking context is created by an HTML element. And then the local stacking context is created by specific properties and the values that you give those properties. Within a local stacking context, the Z-index value of the children are relative to that root element rather than to the document root. And layers outside of an individual stacking context, like sibling elements of a local stacking context, can't sit between layers within another context. So it's all about the stacking context. So if things aren't moving around the way you expect, it's probably because you're not within the right stacking context. So the stacking context rules. Higher values are stacked in front of lower values. That obviously makes sense. That's how Z-index works, how we all know it to work. And then auto Z-index values and elements with the same stacking order, or I'm sorry, with the same value are stacked according to their appearance in the HTML. I have a huge surprise though, and this is where things get complicated with stacking contexts. Z-index isn't the only way to create a stacking context. So if you go into your developer tools and you're inspecting your stacking context, you've gotten this far, and you're looking and you know that things aren't moving around the way you expect because you're outside the stacking context, you might not realize that other properties you're giving things are creating new stacking context as well. So opacity, when its value is anything less than 1. Filter, when its value is anything besides none. Mixed blend mode, which is just affecting for that individual element how the pixels interact there with the pixels on the layer below it, when its value is anything besides normal. And then when you apply a transform to something, so something like scale where you're affecting the size, or translate 3D where you're using the GPU to make transitions smoother, those all create new stacking context in addition to Z-index. So the key to debugging Z-index is to be able to spot when the new stacking contexts are formed in your developer tools. You want to be able to look up the ancestor tree and see if any parents are forming new stacking contexts. And then I have this number, 2,147,483,647. And that, does anybody know what that number is? Thank you, yes. It's a max signed value of a 32-bit integer. So that is a maximum value you can give your Z-index because you actually are limited based on the browser's programming language. So if you're trying to give it a Z-index value of something higher than this, the browser will not let you because it can't. Okay, so going back to the beginning, just to sum things up and wrap everything up. First, the browser is going to construct the DOM by parsing the HTML. Then it goes and requests the CSS and JavaScript resources. But if those scripts are synchronous, which they will be by default, they won't be executed until the CSS is received and the CSS object model is constructed, since it's render blocking. So we complete the CSS object model construction, we unblock the JavaScript engine, then we execute our JavaScript. At that point, we go and merge the DOM and the CSS object model together to create the render tree. After we have the render tree, we run layout, paint, and composite. And finally, I want to leave you with this. So next time we're looking at our CSS and we think, you know, this is dumb, this is magic, why is it behaving this way? I would like to argue that CSS can be reasoned about just like you do your Angular code, just like you do your JavaScript code. You can reason about it systematically, just like everything else. Computers are good at following your instructions, but not at reading your mind. So hope you guys are now feeling a little bit less like this and a little bit more like this. Thank you guys.